Okay, thank you for the introduction. And thank you all for coming back from lunch so quickly. So most of my work actually has been on the effect of bioactive components in cancer. But today I'm going to present a small part on the application of metabolomics to the effect of curcumin in lung cancer. So lung cancer continues to be the the cause of the maximum number of cancer deaths in the United States, as also around the world. And part of this is attributed to late diagnosis of lung cancer, which could be probably one of the reasons could be because of the lack of early biomarkers of the disease, leading to poor prognosis. Also, other factors include some of the treatment regimens, which currently are not as useful for lung cancer prognosis. Also, some of the symptoms of lung cancer, such as the common cold, respiratory troubles such as shortness of breath, weight loss, are often seen in other respiratory diseases, which sometimes overshadows the diagnosis for lung cancer. So looking at the treatment regimens today, most of the drugs which are available for lung cancer treatment include the platinum drugs. And although a number of platinum drugs in combination with different treatment regimens have been documented, there was no additional benefit of any of the drug regimen for non-small cell lung cancer patients. So over the last decade or so, a number of researchers have been looking at different bioactive food components in different diseases, including cancer. And you might have seen several references with lycopene, curcumin, resveratrol, etc. And these have a benefit that they can be used by themselves or in combination with different drugs because they are often synergistic with the drug and sometimes display pleiotropic effects. So in our study, we focused on curcumin, which is a hydrophobic polyphenol extracted from the ground rhizome of the herb Curcuma longa, often referred to as turmeric, and most of you might recognize it as the yellow-colored spice in Asian curries. So curcumin has been known in the cancer world for some time now, and along with the different signal transduction pathways that it perturbs or it goes through, it is seen that curcumin affects or retards tumor cell inhibition at multiple stages. So in the tumor initiation stage, where a normal cell is transformed to a tumor cell, in the proliferation stage, as also at metastasis, and where we have looked at markers such as MMP9 and VEGF, which I won't go through today. But what about its effect on metabolism? So our working hypothesis is that curcumin will cause some inhibition in lung cancer, and the effect on the on lung cancer will be seen as a perturbation in the metabolome, or more correctly, the metabolic profile. And in addition, we also would like to see some potential biomarkers associated with progression of lung cancer. So in order to investigate the anti-cancer effects of curcumin, we took Golden Syrian hamsters. These were male animals, 8 weeks of age, and we divided them into two broad groups: the treatment group, which were induced with lung cancer, and the control group, which were not induced with lung cancer. So the treatment group was further subdivided into two groups: one which was induced with lung cancer using the carcinogen BOP, but they were not provided with any curcumin in their diet. Whereas the T2 group was induced with lung cancer for the first 11 weeks, and after week 12 of the study, they were introduced to a, dietary curcumin at 2% weight. Similarly, the control animals were also divided into the control group, the C0, which was not provided with any curcumin, and the C2 group, which was administered 2% curcumin-containing diet throughout the study. So after sacrifice at week 24, we collected different tissues, plasma, etc. for different assays. However, for the metabolomic analysis, we used the urine samples which were collected weekly. The data presented today is from samples which were collected at week 0 for baseline, week 23 for the end of the study, and some of the data is from the middle of the study, week 11, where curcumin has not been administered. So the cancer incidence itself was confirmed by histological studies. This is an example of a normal lung tissue which was obtained from our control animals, and you see that the alveolar spaces in here are very cleanly laid out, and it's very nice and spaced out. This is with H&E staining, commonly used for different tissue stainings. And as opposed to the lung tissue from the T0 group, which was the one which was induced with BOP for lung cancer, and you see that the tissue is extremely condensed, and there is a tremendous increase in the number of lymphocytes, neutrophils, macrophages, and eosinophils. To validate the presence of adenocarcinoma or atypical cells in these tissues, we further conducted immunohistochemistry and stained the tissue with cytokeratin to look for positive or validation of those atypical cells. So based on the histological evidence, we saw that the incidence of cancer was about 45% in the group which was administered BOP. That means it had lung cancer but was not given any curcumin in the diet, as opposed to the T2 group, which was administered curcumin after week 12 of the study. As would be expected, there was no atypical cells seen in either of the control groups. Cancer was also estimated, or the DNA fragmentation, which is a hallmark of cancer, was also estimated by the COMET assay. So what you do is here you take a lung tissue and treat it in different steps and illuminated using cyber green. And if you see these nice circular unbroken spheres, it means that the DNA fragmentation is not present or is limited, whereas and this was so in the animals which were the control animals, which were not induced with lung cancer. Now, on the other hand, if you look at the slide at the bottom, this is from the animals induced with lung cancer, and you see that the tails of these circles are clearly visible, and the length of the tail, it may not be as clear from there, but just believe me. So the length of the tail actually is proportional to the amount of DNA damage which has occurred. So when we start quantitating that, and this can be done using the software which comes with the software package which comes with the assay, you can quantitate effectively the tail length of these different DNA fragmentation patterns, and we saw that there was a statistical difference between the tail length seen in the T0 group versus the T2, the group which was administered curcumin, and also both of them were significantly higher than that observed in the control groups. I'd like to point out here that we will be using the tail length later on in part of the metabolomics analysis. So then to see if the lung cancer progression does affect urinary metabolomic profile, we followed the following approach. So animals, the urine sample were collected from these hamsters and subjected to NMR spectroscopy. This was done on a 500 variant instrument. And the data was pre-processed using ACD software and binned and digitized and subjected to multivariate analysis. And this analysis was done using the SIMCA P+ software by Umetrics. Also, we wanted to see whether the differences that we see in the metabolomic profile using multivariate analysis in any way correlated with our DNA damage that we measured independently. So to do that, we looked at the PLS plots, and so if we saw that the metabolomic profiles did have some correlation with the DNA damage. And then further, we went to identify and quantify the metabolites using the Genomics library or NMR database. And once we had identified the metabolomics, not biomarkers necessarily, but metabolites, we probed the different biological pathways from which these, to which these metabolites belonged. So just to show you some of the data that we have here. So this is the principal component analysis score plot showing the progression of metabolomic profiles, or the difference in metabolomic profile in going from week 0, that is at baseline, to week 23, which was towards the end of the study. And you see that there is a difference in the grouping of these urinary profiles. So to look at the metabolites responsible for the difference, we turn to the loading plots, which of course are corresponding to the score plots, and we can investigate the particular spectral regions in the NMR or the metabolites for potential biomarkers, maybe for progression of lung cancer. Again, we wanted to compare the animals which were on the control diet versus the animal, both animals in this case were on the control diet or the regular diet, but one were, the control group was not subjected to BOP administration, whereas the T0 group was injected with BOP. So again, we see that there is a significant difference between the metabolomic profiles of these two groups of animals. And again, to look for, which again points out towards changes perhaps due to cancer progression, and we can again investigate the metabolites which are causing the separation or the difference in the metabolomic profiles. Now, the big question is the separation then correlated to the DNA damage, or which is again a hallmark of cancer? So when we plotted the DNA damage in terms of the comet tail length against the metabolomic profile, we see a pretty reasonable correlation of about 0.7. And this gives us a little more confidence in the study. So we saw that the lung cancer progression does lead to changes in proton NMR metabolomic profiles, and that the change that we are looking at is correlated to DNA damage. Now, how do the metabolomic profiles then alter with curcumin administration? So, So this is again a PCA plot, which is from the animals which were given and not given curcumin in their diet. And this was at week 11. That means before the curcumin was provided to the animals. And so you see that in the beginning, or before curcumin was administered, there was no difference in the metabolomic profiles. So after curcumin was provided to these animals, the metabolomic profile shifted with time, and we saw that on the weekly basis. The data presented here is at week 23. And we see that there is a definite separation between the animals which were not provided with curcumin. So this was lung cancer alone versus animals with lung cancer who have been given curcumin in their diet. Again, to look at the effect of curcumin, we turn to the loading plots. And so this group of metabolites, or this part of the spectral region, points out to the effect of curcumin on the lung cancer, and we can explore it further. So we can say that dietary curcumin did cause a change in the proton NMR metabolomic profile in the animals with lung cancer. And actually, I haven't presented the data here, but we also see the difference between the control animals and those on the curcumin diet without lung cancer. So what are these metabolites which were responsible for the changes? And using the Genomics NMR suite, we profiled about 68 different metabolites, of which we found there were 27 which were significantly different between the control group and the lung cancer group. And if you start looking at these metabolites, you will notice that, well, before I go there, I would like to point out here that the trend of the change in concentration for most of the metabolites was as such. So when the concentration, when we looked at the group which was given BOP to induce lung cancer, the concentration of the specific metabolite increased in going from the initial part of the study to the terminal end of the study. And upon curcumin administration, the same metabolite seems to decrease. And this is for 2-oxobutyrate, but also we saw this trend in a lot of other metabolites. And this was significantly different. And so much so that the treatment with curcumin is actually bringing down the concentration of the metabolite closer to the control group levels, which is quite significant. So of the metabolites that we saw that were increased with cancer, we see a lot of the, we see pyruvate, succinate, fumarate, which one of the speakers mentioned earlier, belongs to the TCA cycle, and we have seen that as well. Also, we saw an increase in a number of amino acids. In addition to these, we also saw an increase in branch chain amino acids. And some of these also feed into the citric acid cycle directly or indirectly via different pathways. So it seems that a lot of the metabolites that we were seeing as increasing in the cancer group were leading to the energy cycle. So these cells were using up energy very, very quickly as compared to the control cells or control group. And in the red is highlighted all the different metabolites that we found to be significantly different in the lung cancer treated group as compared to the control group. And some of these metabolites that we saw have already been published and seen by other researchers, such as alanine, glycine, proline have been mentioned before in colorectal cancers as well as other cancer types. Glycine has been seen to be increased in brain tumors, and sarcosine was presented earlier this morning, has been shown to be increased in prostate cancer. Now these are, the prostate cancer ones probably were in the tissue samples and plasma samples, whereas we saw an increase in the urine samples as well. And we did look at some of the other metabolites which were increased, which have not so far being reported to be associated with cancer types. And this might be an interesting investigation to go ahead and look at these in terms of specific markers for lung cancer or cancer in general. So to summarize, curcumin did alleviate lung cancer, and this we saw from the histological studies as well as DNA damage, and curcumin administration led to a decrease in the incidence of lung cancer in these animals. The PCA score plots were significantly different between the treatment groups and the control groups, especially towards the end of the study. The loading plots is where we go and try to see which metabolites are responsible for the difference between the groups. And we were happy to see that the NMR metabolomic profiles correlated well with DNA damage. So in our study, we found 27 metabolites to be significantly different between the control group and the lung cancer group. And some of them have already been seen to have a role, either direct or indirect, in many cancer types. And some of them are still undocumented, and it would be interesting to further investigate them as potential biomarkers, perhaps of cancer in general or lung cancer specifically. I would like to thank my university, Wayne State, for their support. My research group, this was actually the work of Arvind Goja, who has now since graduated, and he's working as a postdoc. Dr. Doina David is a pathologist who had who helped us immensely with grading of the histological slides. And I would like to thank all of you for your kind attention and for being here. Thanks. Yes, curcumin is not extremely bioavailable normally, but we are seeing the effect of it. And there are studies showing the kinetics of curcumin, which even lower concentrations of these 1% in the diet have been shown to become available in tissue level, especially in colorectal cancers they have been shown.
I think your point is interesting, but I think there is a study that shows that curcumin can have an effect on the microbiome in the gut, and then can modify some of the metabolites that are coming in and from the food, and maybe and this way maybe interact with cancers that are not just in the gut. Maybe it's a possible explanation.
To add to that, there is also another study which shows that it affects the gut microflora.
Yes,
so by affecting the gut microflora, in turn it changes the metabolism and goes and changes certain metabolic profiles.
Actually, I was going to ask, related to those questions, with the NMR spectroscopy, do you see curcumin as actually a different molecule in the urine of treated and untreated, or do you find metabolites of curcumin that actually might be related?
Because curcumin is hydrophobic, it doesn't really get into the urine as much, and it is removed in the fecal matter mostly. So we don't see it in the NMRs as such.
Sorry. So I think I can be quite loud as well. So you're having... Oh, I'll be even louder, sure. So, you showed... Wow, echo too. You showed that you're seeing, you mentioned, I think, 27 metabolites that you're seeing change. Mm-hmm. In my experience with urinary metabolomics by NMR, I think this is a problem that I've seen generally, which is that, you can only really measure about maybe 40 or 50 metabolites.
Right.
Are you seeing more metabolites than that?
We saw about, I think the library has almost 300 now. Mm-hmm. Metabolites. So we profiled as many as we could. In this one, we profiled about 100 metabolites, out of which we saw only 27. So it's about a third.
It's about a third. So, yeah. But it seems like you're seeing
there
more.
were some peaks we could not analyze at all. So there are some unknowns.
Really? Okay.
Yes.
So have you tried to tune down your model so that you can only see sort of the most relevant changes, or is that something
like
you could
even do? Like a dose response? Not in the animal model. We have done some in the cell model. So we have done lung cancer cells, and we have looked at different dose responses of curcumin as well as other other bioactive food components like garcinol we've been looking at. So we have some dose response curves, but in cell culture model, not in animals.